The next topic we said we're going to talk about is molecular weight. And more correctly, we're going to talk about average molecular weight. So we've already seen a little bit about molecular weight when we looked at the molecular weight of titanium dioxide. Hopefully you know the difference between atomic weight and molecular weight. Atomic weight is just the mass per mole of an individual atom, whereas molecular weight is the mass per mole of something that's a grouping of atoms like titanium dioxide, water, H2O, etc. So we're going to talk about average molecular weight. And so average molecular weight is denoted by the symbol M with a bar over it, and it should be a capital M. I didn't draw it too well, but M bar is average molecular weight and that is the summation of the mole fraction of what you have. Okay, and it should probably be I equals N or something like that. Forgive me if I'm doing my summation notation poorly, times the molecular weight of an individual species. Okay, so the mole fraction times the molecular weight. And so the example I'm going to use is that of air. Okay, so we said earlier air is 79%. 79% oxygen, or sorry, nitrogen. Excuse me. My mouth wasn't doing what my hands were doing. 21% O2. So nitrogen and oxygen in this form are both diatomic, therefore they're both molecules. So we can use this as a decent example to show folks the concept of average molecular weight. So this ratio applies to volume. And you may remember this from chemistry, but the volumetric ratio of an ideal gas equates to the molar ratio of an ideal gas. So remember that because it comes in handy later in class. Volume ratio and also molar ratio. And again, this is a rule that applies to ideal gases. I'm sure it was named after a scientist whose name I've probably forgotten now. In this case, let's do things in terms of kilogram moles, just to get people familiar with the units. So the way we would write it, so we look at our summation notation, okay? So we have mole fraction times molecular weight, okay? And so we want to set up a summation now. So the molecular weight of air is equal to, so our molar ratio, we can also put slash if we want to keep semantics, or I guess consistent is the word I'm trying to look for. So the average molecular weight of air is the combination or the summation of the mole fraction of nitrogen in air times the molecular weight of nitrogen or diatomic nitrogen plus the mole fraction of oxygen in air times the molecular weight of the diatomic oxygen in the air. And so to write that out quite simply, and it doesn't really matter the units, but we'll just use kilogram moles for funsies. So 0.79, which is the YI of nitrogen, times molecular weight of nitrogen. So there are 28 kilograms, in 1 kilogram mole of N2 plus 0.21, and I probably should put air somewhere and it's not going to cancel, so it gets kind of goofy, but 0.21 moles of O2, and we'll put kilogram moles. Okay, That's the fraction in 1. And I should have put this, so 1. All right. And I should have put 0.79 kilogram moles. So forgive the bookkeeping. This one's a little bit better. Sorry about that. Okay, and there are 32 kilograms of O2 in 1 kilogram mole of diatomic oxygen. Okay, so we've set it up, and I apologize for my poor bookkeeping methodology again, but let's kind of carry it down here. Is equal to 0.79 times 28, and that's, excusez-moi, 22.1, and plus 0.21 times 32, and that's 6.72. And the units, I struggle doing this portion of the course always, and I'm sure there's somebody who knows how to do this a little better than I, maybe even a better YouTube video. But you add them together, and that is equal to 28.82. And so I think in this place it would be kilograms per kilomole, or kilogram mole. And so again, the same rule applies. There's the average molecular weight of air is 28.82 grams per gram mole, and 28.82 pounds mass, pound mass mole. All right.